Good evening, everyone. Welcome back to fifth day of DSA Carnival. I am Rishabh Rathore, your host, a third year student at Indore Institute of Science and Technology. Today, agenda of today's season, the agenda of today's session is linear and binary search. For that, I would like to welcome our guest, Mr. Abhinav Awasthi, currently associate mentor at Geeks for Geeks, founder of CP with Abhinav, a YouTube channel with more than 4K subscriber where he teaches about competitive coding and data structure.
Yeah, hello Rishabh. Thanks for inviting me. Thanks to all the organizing committee of this DSA Carnival. Thanks for inviting me. So today we will start with the topic of searching. Okay, so we understand the concept of searching, the logic behind different algorithm which we use for searching. Okay, so just a comment from your side that I am audible and visible clearly, so that we can just start. Okay. Okay, guys. So we will start with the that what is sorting and what is searching, and we will understand some algorithms which are associated with searching. Fine. So as we all know that the data is basically available in a very large quantity, and it is just randomly available in our databases or in our different things. Okay, but if we talk about searching of a data, for example, there are large code bases. Okay, for example, if you are just making a login into a particular website, so there are millions of usernames. Okay, then when you are entering your email id or your username, so the algorithm behind that particular website first search for your username, then the password associated with it. Such type of things are there. Okay, so for that, obviously we need a searching algorithm. We have to perform searching in a particular form of data. Okay, so today we will be discussing about that searching thing only, and we will discuss some algorithm. So first of all, a very basic algorithm for searching. Okay, can anyone tell me the most basic way how we can perform searching on a series of data? Okay, so to perform a searching on a series of data, we have just that thing that which is known as linear searching. Okay, so if I will just write here that we have an array. Let's consider an array. Okay, we have an array, and let's say that array has some n elements. Okay, or five elements. Let's say in this case it is five elements. The elements are like 5, 7, 3, 2, 9. You have to search for an element that is 2 present in this given array or not. Okay, this is a thing which you have to perform. So the most basic algorithm which you can use to find that is 2 present in this array or not is a linear search. Linear search means that you have to just traverse, iterate through this whole array, and you can just check that the first element is 5, second element is 7, third element is 3, then there is a 2. Yeah, 2 is present. We can say that yeah, 2 is present in this particular array, or we can also return the index of that 2. So this is what linear searching is, that we are just going linearly. Okay, and it is basically in all the linear data sets, just like in array, in vectors, we can use this type of searching, which is linear searching. Okay, uh, for example, if we will search for a number 8, so it will just iterate through the whole array, and it will say that 8 is not present here. As you can see that 8 is not present in this given array. Okay, so this is a concept of linear search. This is a very basic thing. Okay, I've just started from basic thing. Okay, this is what linear searching is. Can anyone tell me a more efficient way? Because okay, so can anyone tell me the time complexity for this linear search? The time complexity for this? So we have to iterate to the whole array. Na? We have to iterate to the whole array. So obviously, we have to make, if there are n elements in that given array, so the time complexity will be O of n, because one has to iterate through all the elements. Yeah, exact. It is O of n. Great. It is O of n. Great. It is O of n. Fine. So, but we can also perform it in a, because O of n is not a very good complexity in terms of searching, because we have to make various searching queries. We have to make various searching queries now. So that is what we have to do. Now let's see, let's understand that for example, uh, this given array is sorted is in a particular order. Okay, so if a data is given to us in a certain order, so obviously that will be more efficient for us to do. For example, you all are given with dictionary. Okay, you all have dictionary, you all have must use now we have Google. Okay, but yeah, when we are in some fifth standard, sixth, so we use basically dictionary to search things when there was no Google, when there was no internet. So at that time, for example, you are just searching for a alphabet D, for example. So first you just open that dictionary and you have that this is alphabet G. So you know that yeah, D is before G. So you just again you have just opened a page which is before G. So you have got yeah, here's a D. Then after D you will search for example, you are searching for discount, the meaning of discount. So for D, then I, D, I, then S. This is the thing which you do basically. This is the very practical example of searching. And you have your whole dictionary, and there you have to search for a word. What if that dictionary is not sorted? Is not, because the dictionary is basically present in a alphabetic order, na? We all know. What if that dictionary is not present in alphabetic order? In that case, you have to check for each and every page of that dictionary. Just think of this and how it will be, how it will be a more work. The time complexity will be often there. Getting, so this is what, so because the content in the dictionary is organized, is in sorted order, is alphabetical order. So that is why we can just search for a word more efficiently, and that is what binary search comes into role. Okay, this is the work of binary search. If our data is organized in a particular order, either increasing order or at the decreasing order, in that case we can apply binary searching there. So now let's search for that thing, that how we can apply that, what is binary searching. Okay, let's first we will understand the meaning of each and every algorithm, for example linear search, binary search, and also we will just discuss some basic applications of these algorithms. Fine, so till now is everything clear? Is everything clear now? Just a yes in the chat box, and we will continue with the binary search. Okay, great. Fine. So now we'll discuss binary search. Great, 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 guys. Okay. So for binary search, the first condition is that our array or our data, anything, it can be array, it can be vector, it can be any other linear data structure. Okay, it should be in sorted order. It can be increasing order, it can be non-decreasing, it can be non-increasing, any order, but it should be in a sorted order. Fine, getting fine, great. We will also discuss a problem where the given array is not sorted. I'm not means it is not sorted in a it is basically it is arranged in a particular order, but it is not sorted. We will discuss that problem too, and how we can apply binary search there. That is also what we will discuss today. Okay, we will have some problems in the last of the session, which are good problems, which are amazing problems. Okay, fine. So for example, the data given to us is in let's say in non-decreasing order. Okay, non-decreasing order. So the data is 2, 3, 4, 4, 5, 6, 7, 8, 9. This is our data. Okay, so we have to apply binary search here. Binary search. So now let's understand how this algorithm works basically. Okay, so let's say that our number the number which we have to search for is something like, let's say we are searching for the number 7. Okay, let's say that we are searching for the number 7. No problem. Okay, so to search for 7, what we basically do is that in algorithm of linear search, what we do, that we basically start from the first index, then we iterate, then we move towards the later indexes of our array. Okay, that is what we do in case of this particular linear search. But because we have our binary search algorithm, so what we will do, we will not iterate through all the array. We will have here, this will be our start pointer, and this will be our end pointer. Means this is the start. So basically what we do in binary search, after every operation, after every iteration, what we do, we take a different subarray. We will just understand it, okay? So for example, this is the start point, which is the start point of the given array, and this is the end point, okay? That is what is given to us, fine. So now we will find the mid of this array. So this is the midpoint, you can see. The mid can be simply like mid is equal to start plus end by 2, or there are different meanings also, fine, of to initialize mid, okay? So we will write its code and we will understand, okay? Great, great, fine. So now what we will do is that this is our mid, fine. So now we have our mid, we have our data arranged in a sorted order, which is here it is a non-decreasing order. It is not a non-decreasing order, fine. It is not increasing. It is not increasing because there are equal elements too, but it is a non-decreasing order, fine. This is what it is, okay? Great, great. Now we have our mid element is, if we talk about mid element, it is 5, and we are searching for 7. So there is an observation we have got, that because 7 is greater than 5, so it should be always in the right of this mid. Obviously, because it is in a non-decreasing order, and 7 is greater than 5, so obviously it is in the right side. Or basically, if we divide this whole array into two sub-arrays, first is the left side of this given whole array, and this is the right side. So if I will just tell you that where does this 7 lies, so you can just say that, sir, because 7 is greater than 5, so it should lie on the right side of the array, right side of the mid basically. So now in the, because but till now we have not got our 7. We have not got our 7. Just we have observed one thing, that 7 will be at the right side of this mid. Okay, that is the thing which we have observed. Great, great. Now what we will do in the second iteration, because it is a iterative manner. Now this is a binary search is in a iterative manner, also in recursive manner also, but we will code in an iterative manner. We will have loops for that, probably a while loop. Okay. So now for the next iteration, we will use this particular subarray as our array. Getting? So now you can see that the whole array is reduced to its half, and then in the next operation it will again reduce to its half. Getting? And then at the final chance we will get our 7, that is 7% or not. We can just easily get it. Getting? Fine. So now, is this thing clear, everyone? Great. Okay. Okay. Great, guys. Now listen, okay. So in the last iteration, our start point was here, and our end point was here, and this was our mid. Okay, this was our mid. Now the thing is, now we have to consider this particular array. So because we have to consider this given array, so our start will be here. So basically, start will become mid plus 1. Start will become mid plus 1, and end will be as it is. End will be as it is. Getting? Fine, fine. Now again you will find a mid. So here, if you will see that mid is 7 only. So because mid is 7 only, we can just say that yeah, 7 is present, because now mid is equal to the number which we are finding. Now mid is equal to the number which we are finding. Na? So in that case, there is no problem. In that case, we can just take it. Okay. Great, great. Now, for example, we are searching for 3. That is also okay that we are searching for 3. So for 3, because 3 was less than our mid, in the first iteration, 3 was less than our mid. 7 was greater than, but 3 was less than our mid element. Okay. So in that case, what we can do? In that case, we can just consider this particular subarray. And this subarray will has its start as it is, and its end will be basically mid minus 1. This will be its end. Okay, so this is how we basically code this thing, and we basically apply binary search algorithm on a given piece of data which is in a sorted order. That is a thing which we have to consider. Okay, which we have to discuss. Fine. So obviously that it is more efficient. So can anyone tell me the time complexity for this uh, algorithm? If anyone knows the time complexity for this binary search algorithm, anyone who can tell me? Exactly, exactly. It is something of O of log base 2n. Okay, so it is something of O of log base 2n. Okay, why it is like this? Because you see that in each iteration we are dividing the size of our array to be considered by 2. Fine, yeah, exactly, Arman Hitans. Great, great. Okay, so this is what we can just understand from this given example of a binary search. Okay, so now we will just move towards the code part. Okay, and we will also understand the code, how we can basically solve this given problem, and we can just go through it. Okay, great, guys. So here, this is the thing. We have our editor here. Okay, so let's code our approach. So first we will just code our linear search. Okay, so linear search is something of a very simple algorithm. Just for example, let's consider that we will have a int array of size n. Okay, that is what we will have. So we have to apply binary and we have to search for a element x. That is what we have to search. Okay, so for that, simply what we can do is that let me just zoom it for you guys. Okay, yeah, great. Now what we can do is that we can just iterate, we can just use a for loop. Okay, to iterate through this given array. Okay, and if that given element is equal to our element, we have to just return true. That, yeah, that element is present. That is a simple linear sort algorithm, linear search algorithm. Sorry, I'm just saying sorting as search of sorting. Sorry. Okay, great. Now we have to, for example, we have to write the binary search code. Binary search code. Okay, great. So for binary searching, what we can do is that, as I told you, that we will have some extra iterators, which is the start iterator and the end iterator. Okay, that is what we will have. So there we will be like int start, and start will be the start of the array, which will be 0 only. Okay, and we will have a int end, that will be the last index of the array, which is n minus 1. Okay, great, fine. Now what we will have is that we have to traverse basically, and guys, the thing is that till where we will iterate. So we will iterate till this index start is less than this index end. That is the thing. Okay, because they cannot overlap or intersect each other. Na, that start is greater than end. Fine. If that is the case, that start is making greater than end, that means that element is not present. Otherwise, it should be found. So we will just write that while this start is less than equal to end, till then only we will apply. We will run our loop. Okay. Till then only we will run our loop. Then what we will do is that we will have our condition. Okay, that our mid, how we can find mid. So for finding mid, there are different ways. We can just write simply start plus end. Okay, and we will just take the average of this start and end. That will give us or we can do it like int mid is equal to uh, start plus, and then and minus start by 2. There are different ways how someone declares mid, but they all will give the same result. Okay, fine. So we're just taking one of that. Okay. Now what we will do is that fine. Now what we'll do that we will have some conditions. Okay, so because we have to compare the mid element of this particular array. So we'll just write that if this mid, or we can say ARR mid, is greater than x. Okay, is greater than x. So the thing is that just I want this reply from your side, that if array mid is greater than x, then we have to compare the left side of the array or the right side of the array. Okay, the left side or the right side. And similarly, we will have else if, second condition, that else if arr mid is less than x. And the else condition will be obviously that the arr is equal to x. So if it is equal to x, then we have to just return true. In first case, go left. Exactly. If mid element is greater than the element we have to search for, that means the present element which we are searching is in the left. Okay, because that is in a increasing order. But guys, I have not told you that that the array is given in increasing order. Okay, so that is the thing which you have to observe, that if the array is given is in decreasing order or in non-increasing order, then you have to take the right if it is the case. Now that is what how you can just modify the code. That how you can modify the code, and that is why you are learning, because no one is going to ask you binary search. Okay, no one is going to ask you binary search in basically uh, in any interview or directly binary search problem. They will just twist the problem, they will just modify the problem in such a way that you have to first observe that, yeah, here yeah, here we have to apply binary search. That is what you have to think. Then you have to apply binary search. No one is going to ask that that go and write the binary search algorithm. Okay, that is what your observation skills is. That we have to observe that, yeah, in this question we have to apply binary search, and this is how we have to apply binary search. Fine, great. Yeah. So now here, as you all told you, that we have to take the mid of the left side of the mid. So for taking that, our start will be as it is, and our end will be mid minus 1. Okay. And for taking right, so here we are taking the mid, the left part, and here it should be, for the right part, it should be start is equal to mid plus 1. So this is our binary search algorithm code. Okay, which we can do, which we can solve basically. Okay, and this is how we can just implement a code. And as you all told, that the time complexity for this binary search code is something of O of log 2n. Okay, it is of O of log 2n. There are some other implementations of this too. The implementations, like we can found lower bound, we can found upper bound too. Okay, we can find the insertion index position of a number in a sorted array. Okay, that are other implementations. Okay, let me just share that thing. Okay, let me just explain you guys that thing and how we can just solve that. Okay, yeah, great guys, great. Okay, cool. Yeah. So what now what we will do, for example, you have to find that you have to insert a element. There is a problem. Okay, insert an element in a sorted array, so that the array remains sorted. For example, that the array is 2, 9, 11, 15. Okay, and we have to insert a number 10 in this given array. So this should be the position of 10. Here 10 should be inserted, which is, you can see the third position. Or if it is 0 bias, so it is 0, it is 1, it is 2. Second position. Okay, this is what you have to find. So the brute force approach will be simply like that. You will just iterate from left, and whenever you will got that the next element is greater than 10, then you will just insert it. That is the thing. We can just simply write it that we will take a for loop which will be int from I. If the array is arr and size is I, so it will be from 0 up to n, and it will be I plus plus. Okay, and the thing is that if that given arr I is greater than the element to be inserted, which is x. So we just write that the position is I. At I position, that element should be inserted. Is this thing clear or not? This thing is clear now? Fine. So the thing is that how we can solve this, because this will take O of n. Okay, and obviously this 10 is not present currently. We have to insert it. So we cannot also apply binary search to search for 10. Then what we will search for? Then what we will search for? That is also a thing that we can just do. Okay? That is also a thing which we can just do using binary sort only. Using binary sort only. This is something called upper bound and lower bound. We will first understand the concept of upper bound and lower bound. Okay, and then we'll just come back again to this problem to understand the logic, how we can apply upper bound logic here to solve this particular problem. Okay, great. So what is upper bound, what is lower bound? Let's take a array which is 1 2 3 3 3 4 4 5 6 6. Let's say that this is our array. Okay, so what is lower bound? Lower bound tells us the first occurrence of a number which is, just focus on the words, which is not less than, the given number. We have to focus on this thing, not less than, because some people confuse that we in lower bound we basically found for number which are equal to the given number. That is not the case. Here we have to found a number which is not less than. It can be equal also, it can be greater than also, but it cannot be less than the number. For example, if I will just, and this is for example zero bias. Okay, this is zero bias indexing array. So we have this type of element indexes here. Okay, now guys, can anyone tell me that what will be the lower bound of 4 in this given array? And also I want from you guys, what will be the upper bound of 4 in this array? Okay, upper bound is basically, I will just maybe, let me write upper bound also. For upper bound also, upper bound is basically same thing, first occurrence of number which is greater than. Here it is greater than, this is greater than, instead of not less than we will have greater than. That is what upper bound is. Okay, so can anyone tell me what will be the lower bound of 4 and what will be the upper bound of 4? Exactly, lower bound of 4 will be 5. Why? Because lower bound is basically first occurrence of number which is not, in lower bound basically returns the index of that number. Okay, yeah. So lower bound of 4 will be 4 itself. Exactly, great guys. Right, great. Okay, and its index is 5, so it will return 5. And similarly for upper bound, it will give us the first occurrence of number which is greater than the given number. So the number which is greater than is 5 and its index is 7, so it will return 7. Great. This is what lower bound and upper bound basically does for us. Okay, if you guys just want me to just it, there is a very slight modification in the code of that binary search which will help us to write the code of upper bound and lower bound. A very slight change is there, a very slight change. Okay, let me just explain that thing too. Okay, so what here we are doing is, here we are searching for that number. We don't have to search for that number, so just remove this condition which is else. Okay, fine. For example, first we will write for lower bound. So for lower bound, we want a number which is not less than that number. So if the given number is less than, then it will be something like, okay, just update it. And if it is greater than or equal to, you just write equal to here itself. And so this is what we want. But we will want the first occurrence of it. But we want the first occurrence of number such that it is greater than or equal to x. So we can just write here, we can just take a variable, let's say int lower bound. Okay, basically in C++ there is an inbuilt function also called lower bound, but because in Java we don't have, so there we have to just write the whole algorithm just like we do in binary search. Okay, so we can just write that it will be answer will be, or let's say lower bound will be the minimum of lower bound means its value and the current value made. Okay, let's make it infinity. Okay, this is what we will do. So it will just store the first occurrence. Why I'm taking the minimum? Because I want the first occurrence of such character. Because there will be multiple characters such that they are greater than or equal to x. But we want its first occurrence. So first occurrence means the minimum index, the character with minimum index. That is why I'm placing here. Okay. So this is how we can implement lower bound. If this lower bound implementation is clear, just a yes in the chat box and we will go towards the upper bound. Great, great. Okay. So for upper bound 2, what we will do? For upper bound, we don't want, for upper bound, we don't want repeat, Mayank. Okay. Mayank, what we are doing is that here, we were, in the case of binary search, we were just searching for an element. So that is why we were having a else condition where if that element is present, we are just searching for it. Okay. Great. In this case, what we are doing here, in this case, in lower bound, we want a number which is not less than, means it is either greater than or equal to that number x. So here is the condition that yeah, we have found a number whose position is mid and which is greater than or equal to x. So that is the required number which we are requiring. But we want the first occurrence of that number. So there may be multiple such numbers now whose you can say uh, who are greater than and equal to x. So for that, we can just, we are taking a minimum also. So that we can, and obviously it will give the minimum only. If we will just remove it now, then also it will give the correct answer. But for better understanding, how we can find the first occurrence, I'm telling you. But if I will just remove this, then also it will give us the first occurrence. Okay. Getting? If I will just remove it now, if I will just write it that lower bound is equal to mid, then also it will give us the right answer. Because after checking for this element, it will check for the left subarray. So if there will be a element present in the left also which is less than equal to no, maybe it will not give us because it is left. So yeah, exactly, got it. Fine. So but because for better, so that to avoid any type of mistake, okay, because how the algorithm is working, we don't know about that now. So for that, what we do that we will just take it and we will write it minimum here, okay, so that we can solve. Great, fine. And in the case of upper bound, we will just okay. And in upper bound case, what we want is that we want a number greater than. So I will just remove this equal to from here and apply this equal to here. Fine. And we can just write in place of this lower bound, I can just write upper bound, and that is the case. Means you may find a better implementation of upper bound and lower bound. Maybe you can find a better implementation on different websites on DFG, obviously. But because here I am modifying that binary search to upper bound, lower bound, upper bound and lower bound. So maybe the code is quite confusing because I'm just transforming that binary search algorithm. Nah. But if you will just search for this whole algorithm, you will easily find it. Okay, on GFG or any other. Great. Fine. I hope that this thing is clear. I hope that this thing is clear. Hmm? Okay, great guys, great. So now we will have we will just move towards that problem only, which I have discussed. Okay, and then we will. This was the problem, na? So here, what we can do here, if we have to insert the element, so can anyone tell her what we have to find to insert the element? What we have to find? That what will be the insert position of an element in a sorted array? We have to insert an element in a sorted array. Then what we can find so that we can get the insert position of the element in the sorted array. Okay, that is what if you guys can tell. So we will just move it on, and then we will understand. We will discuss some. Yeah, both lower bound and upper bound work. Exactly. Great, Arman. Great. Okay. Both will work. Because if there will be lower bound, then also it will give us an index which has 10. So in place of 10 also we can insert 10. Na? And for upper bound also. You can just, you all can just try this problem, okay? By your own. Also, we can also use upper bound and lower bound to check that whether a number is present or not in the array. That is also a application of upper bound and lower bound, how we can use it. For example, here you can see that the lower bound of this 4 was 5 and the upper bound of this 4 was 7. Okay, this was the case. Let's say that we don't have this 4 here. Just assume. So the it will be like this. We don't have any 4 here. Okay, so now can anyone tell me, can anyone tell me the upper bound and lower bound of 4? The lower bound and upper bound of 4? Fine. So upper bound and lower bound can be used for searching purpose also, to search that an element is present there or not. So because in exactly great. Yeah, so it will be 5 5. I think, man, you are discussing for that last arena, but yeah, I have just removed that. No, not same as before. Now it will be no Sushma, and now it will be 5, na? Because what I told you, for lower bound, the number should be not less than. It can be equal to or it can be greater than. So if equal is not present, so we will consider greater number. So in this case, upper bound will also be 4, 5, means index of upper bound, lower bound. Na? Yeah, Mayank, but I have updated the index now. I have updated it. So now the index are 5 here. Okay. So lower bound is also 5 and upper bound is also 5. So the conclusion is that if lower bound is equal to upper bound, that means number is not present. Otherwise, if it is not equal to, then it is present. Okay, great. This is the another implementation of binary search. How we can use binary search, how we can use binary search to solve different problems. Okay, guys. So now another amazing problem for you guys, and I will just want answer from you that how we can solve it. Okay, so just first read the problem statement. The problem statement is we are given with a sorted array. You are given with a sorted array. Okay, and in that sorted array we have duplicate numbers also, duplicate elements are also there, and you have to find a frequency of a given element x, let's say. Okay, so for example, that arrays 1 1 2 3 3 3 3 4 5 6 6, this is the array. We have to find a frequency of, let's say, x is 3. So we have to find a frequency of 3 in this given array. Okay, great. Hitans is saying that map, then find. Okay, Hitans, great. So map, we can just use map. Okay, map data structure. So that map data structure will take a space complexity of O of n, and the time complexity will also be O of n, because we have to iterate through this whole array. Na? That is a very brute force solution, Hitans. Can we do it in more efficient way? Can we do it in with time complexity of O of log n? Can we do it like this? Whenever you are just founding the log n thing, that means that the log n base student, that there should be a implementation of binary search. Just just remember this thing. If there is log n, then probably in most of the cases you will have to encounter binary search. Okay, great. So here, as you are, Arman, Jatin, great guys. That is what we will do. That we can just subtract lower bound with upper bound. So if I will just write indexes to all the numbers, so the upper bound of x, means here in this case x is 3, will be this particular index, which is 7, and lower bound will be this particular 7, which is 3. And if I will just subtract this 7 minus 3, I will get 4, and this 4 is our answer. That frequency of this given number is 4. Fine. This is a thing, this is a great thing, and this is a very great implementation of this binary search algorithm. So firstly, what you will say, for example, you are appearing for an interview. So and an interview is just asking you this particular problem. So the first reaction everyone will think of is like that you will say, we can use map, we can use this, because obviously for all the frequency problem which we have solved till yet are solvable by map only. Okay, but what the thing is, guys, is that in real world, in real industry, when you will work for some particular organization, what they want is that the firstly is time complexity. Time complexity is okay, fine. Time complexity is surely okay. Means we have to make time complexity more efficient, but they also think about the space complexity. So if you will use map to store frequency and then you are just doing data, so it will take more space. More space means the more complex version of the software. Okay, so that is why we basically take, maybe in some of the cases when we are not taking space, time complexity little bit high, but that is also preferred. So here in this case also you can see, but for now we don't think about the space complexity. Obviously, in dynamic programming algorithms we have large space complexities, but to reduce time complexity we use it. Okay, so this problem can be solved by time complexity of O of log base 2n and space complexity of O of 1 only, not more than that. This problem is clear to everyone? Just yes in the chat box, then we move towards the next problem. Great guys. Okay. Huh. So now it will be, the thing is one more problem, which is a rotated sorted array, a very basic, a very common problem. As I told you, that in some of the cases the array is not so sorted, but it is organized in a particular way. For example, this is a sorted array. Let's just take simple. Sorry, from 1, 2, 3, 4, 5, 6, 7, 8. Let's take the simple array. Okay, but let's make some modification on this. Let's shift it leftwards 3 times. So when we shift this 3 times to left, it will be something like Fine. This is a thing. And for example, you are provided with a rotated sorted array. Means they have told you that you are that the firstly the array is sorted. They will tell you that there is a sorted array, and we have left shifted, we have left rotated that array by k times, by k times. They will say you this thing, and they will ask that what is the value of k. So in this case, can you tell us what is the value of k? Obviously, we have left rotated this value, this array 3 times. Okay, so the value of k is 3. But how you can find it? The one method is that you can just iterate, and whenever you will encounter a thing that yeah, the next element is gets. This is the brute force approach. Okay, that if the next element is less than the given element, that means that yeah, obviously there will be the partition, and we will just return the value using the index. But that will take O of n time. Is the problem clear, guys? Is the problem clear? No? Problem is clear or not? So how can we solve it? Because this will take this brute force approach will take O of n, but probably we want it to solve in O of log base 2n, because yeah, this is a so we are discussing about binary sets. Now, so obviously we will just think of something which can be solved by binary sets and which can be solved by O of log base 2n. Okay, that is what our real implementation of binary sets is. Okay. So in this case, what we will do is, guys, that we the normal binary search algorithm will not work, uh, because here we have to find this pivot point. We said basically at the pivot point, and this is what we have to find, and which is something like this. This index means from here we have to make rotations, or we have to find that this k. Okay. So for that, what we will do, we will again perform that. Uh, Binary search algorithm. We will implement that too, but in a different manner. Guys, the manner is that here we will have the same thing. We will have the mid. We will have the mid, surely. But what will be the conditions of mid? Okay, just listen, guys. Okay, we will also consider our element, which is the in first element. In this case, first element is 6. You can see. This is the first element. Okay, and what we have to find? We have to find this point from where rotation is done. Because if we have got this point, we can easily find a value of k. Because k will be basically the I plus 1. If index of this point is 2, so k is 2 plus 1, 3. We can easily find the value of k. Fine. Great, great. So we will have this first. Okay. Now what we will do is that we can just write the conditions. So the condition will be that if R mid is less than this first. There's also one more condition for less complexity, otherwise the problem will become more complex. That all the numbers are unique numbers, means there are no duplicate numbers. Okay, let's assume that all are distinct numbers. Okay, so if our mid element, where because as we know that in binary search we take a mid element and then we compare that mid element, and accordingly we will just update the value of start and end iterator. Okay, so if mid element is less than first, what does it mean? What does it mean? If mid element is less than the first element, and what does it mean? It means that our pivot point is in the left of that mid. You can just search it. For example, in this case, mid will be something here or here. This will be the mid. Okay, this is the start point and this is the end point. This is the mid. Okay, and this is the first character. So obviously that if our mid is less than, if our mid is less than our first character, that means our pivot point is in the left side. Fine. So it means that we have to consider a left subarray of that mid, the left part of that mid. And else, if that mid is greater to the first, okay, if that is greater to the first, For example, our mid is something like here. So it means that the pivot point is in the right side. You can see the pivot point is in the right side. So we will call for right. Okay, so this is how we basically search for this problem. Similarly, the given problem can be, you can say, modified in different ways, guys. Now we can either cyclically rotate it. Cyclic rotation, this is what this is. We can, here it is rotating leftwise. It can rotate as right side. Okay, that is also we can do. Fine. So this is how we can just solve this problem. We can just implement that, how we can implement use binary search algorithm to solve different problems. Okay, because guys, in this problem, if someone will just see it, okay, so it is very difficult to understand that, yeah, we have to apply binary search here now. But yeah, we can here, and we have just checked how we can apply now. Yeah, okay, thanks very much. Great. So now, similarly, here what we were searching for a pivot point, the value of k with means the number of rotations which we have done. We can also perform searching in this rotated sorted array too. We can also perform searching. So for that searching, obviously, what we can do is that we can just slightly change the algorithm of our binary search. The algorithm will be as it is. Just when the array is sorted, so we have to also make a reference of the first character. As I told you, na, that if our current element is less than the first character, that means it is in the second half. Second half means this is first half. First half means the rotated half, which has come from end, and this is second half. So if our mid element is less than the first element, that is we are at the second half or the second part of the array. And if that element is greater than, for example, this 7, that means we are in the first half. This is how we can also perform sorting here too. We can also perform sorting. Okay, this is what binary search is. Okay, similarly, guys, we have ternary search too. Okay, we have ternary search too. So in ternary search, as the name suggests, it is just similar to binary search. It is just similar to binary search. Okay, as the name suggests, for example, we have 1 2 3 4 5 6 7 8 9 10 11. Okay, and so here, in case of one mid, we have two mids. Okay, which will divide the array into three equal halves. For example, for in this case, the first mid is here, the second mid is here. This is mid 1, and this is mid 2. So the normal conditions are that if that x is less than mid 1, then it will be in the first part. If x is greater than mid 2, that means it is in this particular part. And if x is else, means it is not less than mid 1, it is not greater than mid 2, so it will be in the middle part. So it is just a modified version of binary search, where we can just divide this ternary search into three parts. So in each iteration, the array is divided into three sections. Just like in binary search, we are divided into two sections. Can anyone tell me the time complexity for ternary search? Then we will discuss its code. Time complexity for ternary search. Okay, and then we will discuss its code. Thanks, Akanksha. Thanks. So the time complexity for ternary search, guys, is basically O of log base 3n. Here base will be 3, because in each step the array is divided into three parts. Okay, so that is what we can do, guys. Just a minute. Yeah, great, great. So, and then here in this ternary search, we are basically dividing that array in that we have two mids. Okay, and the same condition is there for R and L. Okay, and then we are just checking that if key is equal to the both of the mids, then we can just return the mid value, and then the exact condition which we have discussed, that if k is less than mid, then it will be in the first, it will lie between first and mid one. It is greater than mid 2, then it will lie in the third part, otherwise it lies in the middle part. This is a simple uh, ternary search approach, ternary search algorithm, and ternary search is basically used less, okay, because it has its own. It is basically because here the thing is that in ternary search we have more comparison. The first comparison here, second comparison, third comparison, fourth comparison, fifth comparison. So maybe you will think that yeah, ternary search is taking O of log base 3n. The time complexity is less. Maybe you will think that sir, the time complexity of ternary search is less than binary search, obviously. So we should use this. Okay, we should use this ternary search algorithm. But because here comparisons are more than the binary search, that is why overall ternary search is quite slow or same. So overall, the most efficient one is binary search, and that is why we basically use it. Okay, Gaurav, I hope you have got it. That is why we use binary search in our thing. Okay, this is the thing, guys. So this is our session on uh, searching. Okay, so we have discussed how our binary search works. No, binary search is not. Yeah, exactly. The time complexity of binary search, Arman, is I can say that is greater than of ternary search. But because ternary search has more comparisons, okay, so that is why we prefer binary search, no? As I told you. Okay, yeah. Thanks, Ridhima. Thanks. Okay, yeah. So now, guys, any doubt from your side? You all can ask your doubt, and then we can just complete. Okay. Great, guys. Great. I hope the session is helpful for you guys. It is informative, and you guys have learned something about something new about searching, all the algorithms, how we can implement, how we can the more applications of the searching. Okay. I hope you guys know about that, and great, great, guys. Great. Thanks, Imansu. Thanks. Thanks, Naman. Thanks, Arman. Thanks, Archita. How to be consistent in coding. Gaurav, just practice daily. Just practice daily. Okay. And try to make some interest in coding. That is the way how you can be consistent. Okay. Thank you, guys. Thank you.
Thank you so much, sir, for conducting such an informative session. DSA Carnival, grateful to you for accepting our invitation for very short period of time. I also thanks to our title sponsor Geeks for Geeks and education partner Coding Minutes for being a team of DSA Carnival.
Thank you. Thank you, Rishabh. Thank you, guys. Thank you.
Guys, now it's time to show up your skills by giving a quiz. The quiz link will be open for next 10 minutes. You have chance to win some amazing goodies and swags. So get ready. The link will be in the description soon. Thank you.
So you think you know data structures well, but often get stuck when it comes to problem solving. Well, now you are at the right place. Welcome to Data Structures and Algorithms Level Up course. Hi, my name is Prateek and I'm a software engineer at Google. I have created this course for anyone who wants to learn how to apply data structures for solving coding problems and algorithmic optimization. In the past 5 years, I have taught over thousands of developers through my online and in person bootcamps. that helped many students and working professionals in their careers immensely. This course will help you to develop a strong problem solving mindset and write cleaner and highly optimized code. This course is a highly practical course, and we will discuss over 100 problems of varying difficulty levels along with a complete hands on implementation. You will learn various tips and tricks related to concepts like recursion, backtracking, sliding window, two pointer problems, dynamic programming, pattern matching, graph algorithms, and more. Not just that, you will also learn by solving problems involving various data structures such as stacks, queues, linked lists, heaps, hash tables, tries, and graphs. With over 200 plus high quality video lectures, concise and simplified explanations for complex topics, this course is your one stop destination to master problem solving. Unlike most other courses, this course is fully interactive. You also get coding exercises and multiple choice questions to test your skills. The code judge ensures that your logic is correct and you get a real time feedback on your code submission. Doesn't matter whether you have a computer science background or not. This course is for anyone who wants to ace problem solving and achieve big. So what are you waiting for? Sign up today and I'm looking forward to meet you in the course.